Thank you, Justin, for your wonderful presentation. Coming up for the next 15 minutes, we will have our third speaker, Jonathan Cheng Lin, who is currently pursuing his Master in Engineering at Swinburne University of Technology, Sarawak. His presentation today is Pyrolysis of empty fruit branches, lignin extract using Sucrose-malic acid water low transition temperature mixture. Without further ado, I will pass the stage to Jonathan.
A very good morning to everyone. My name is Jonathan Cheng from Swinburne University of Technology. The topic that I will be talking about today is the thermogravimetric analysis and combined kinetic study on the pyrolysis of empty fruit bunches lignin extracted using sucrose-malic acid water low transcendental temperature mixture. Yeah, so for the background, global consumption of and dependency on fossil fuel has skyrocketed in the last century. Energy demand in Malaysia alone has increased from 80 megatons of oil equivalent to 36 megatons of oil equivalent in the last 20 years, and it is forecasted to increase until 89 megatons of oil equivalent in 2050. Fossil fuel still dominates the majority of energy production in Malaysia. Continuous reliance on non-renewable energy sources such as fossil fuel will lead to environmental issues such as air pollution and climate change. Malaysia is a country that thrives on agricultural activities, and oil palm is one of the national cash crops in Malaysia. Malaysia generates an average of 84.74 million metric tons of oil palm biomass annually. Oil palm biomass can be categorized into 5 main types, which are oil palm frond, oil palm trunk, empty fruit bunches, palm kernel shells, and mesocarp fiber. These oil palm biomasses are made out of lignocellulosic biomass, which are cellulose, hemicellulose, lignin, and extractives. Current processes mainly focuses on using the polysaccharide fractions, which are the hemicellulose and cellulose part, in their thermochemical processing. For example, gasification, wet torrefaction, combustion. Polysaccharide fractions then means that they only focuses on cellulose and hemicellulose. So what about the lignin? They will go as far as to to extract the lignin in order to enhance the product of the thermochemical processing. The lignin, after the extraction process, the lignin is considered as a byproduct and will be normally discarded. It is no longer a wise choice to discard lignin, as lignin, being one of the largest sources of aromatic, it has a good potential as a feedstock for other thermochemical processing, which we can say pyrolysis. Yeah, so lignin can serve as pyrolysis can serve as a tool to utilize the unwanted lignin. Pyrolysis is the decomposition of biomass brought about by high temperatures under oxygen deficient environment. Every type of biomass has its own different thermal degradation behavior and products characteristics. Therefore, it is important to find out the thermal degradation behavior of the extracted lignin of EFB. Now, how do we extract the lignin? Lignin is extracted to, normally there are three types of extraction method which we'll be using mid liquids, deep exotic solvents, DES, and this low transcendental temperature mixture. LTTM has an advantage as it is a greener and more affordable type of solvent. It Its benefits include water compatibility, low vapor pressure, low flammability, biocompatibility, and biodegradability. Yeah, so using this LTTM, I will be using it to extract my lignin from EFB. Yeah, so moving on to my methodology. First, after I collected my EFB, I will put it in the oven to dry at 105 degrees Celsius to remove the moisture for 24 hours. After that, the EFB will be put into a sieve shaker, and then it will be milled and then sieved to a desired particle size of 500 to 1000 micrometer. After that, you will put into a seal bag and store in a desiccator to prevent more moisture from getting in. So how do I synthesize my LTTM? I will mix malic acid, sucrose, and water with a molar ratio of 2:4:2 and place it in a beaker on a hot plate. I will keep the temperature at 60 degrees Celsius for 15 to 30 minutes or until my LTTM is clear or transparent in appearance. This is the LTTM before synthesis, and this is after synthesis. You can see that there is no more solid particles inside. So for my lignin extraction, the lignin is then placed inside the beaker here, and then placed into the O-bath here. The O-bath will be set up as like this. The operating parameters that I'll be using is the temperature is 100 degrees Celsius. The biomass to LTTM ratio is 1 to 20, and the treatment duration is 6 hours. For the extraction, this is after the extraction process. You can see that there is 3 layers here. On the top layer, that is the lignin. This is after I add in distilled water for the precipitation. The lignin will precipitate on top. You can see that there is a layer here. Yeah, so after that, after the lignin has been collected, it will be dried in an oven, refiltered, and then dried in an oven, and then harvested. I will do pyrolysis, TGA analysis using the simultaneous thermogravimetric analyzer, and this is an example of the thermograms that will be collected. After that, I have done my TGA analysis, the data collector will be used in kinetic modeling. I will be using model 3 and then model 15 together. First, I'll be using the TGA data and plug it into the a.k.a. Sunos model, the CAS model. This is the model here. It will be used to determine the activation energy. The activation energy here will then be placed into the model 15, which is the Sestad burden model. This is to determine the reaction mechanisms, which is MNP, also known as diffusion, phase boundary reaction, and then nucleation. Yeah, for my results and data analysis, this is the thermogram for the lignin pyrolysis. This is the TG curve. This is the DTG curve. As you can see here, the TG curve, they underwent a steep thermal degradation between 136 degrees Celsius to 750 degrees Celsius. It increases as I increase the heating rate from 5, 10, 15, 20 degrees Celsius per minute, the TG curve shifts to the higher temperature when the heating rate varies from 5 to 20 degrees Celsius per minute. The increase in heating rate translates to a delay the increase in heating rate translates to a delayed thermal degradation as the temperature difference between the surface and the center of the sample particles is wider. The DTJ curve illustrates that the total number of major processes happening in the major thermal events happening in the process, while each peak represents a different reaction happening in the pyrolysis. The massive weight loss peak here represents the devolatilization of the lignin. Afterwards, the result gathered here, the data gathered here will be plugged into the test model. This is the KS model that has been plotted out. This is the conversion factor. The conversion factor will be, conversion range will be put into 0.1 to 0.8. This is the linear equation generated. This will be averaged out, and then the average activation energy was found was 66.68 kilojoule per mole. This means that the pyrolysis will use 66.68 kilojoule to activate. So after that, the activation energy was plugged into the Sucrose-malic model to find the NMP. We found that the pyrolysis of extracted lignin from EFP was mainly dominated by diffusion reaction, as it is shown here. It was also calculated that adjusted R squared is more than 0.98%, which means that the fitting is hiding. For the research impacts, it had successfully extracted lignin from EFP using sucrose-malic acid, water, LTTM. We have explored the thermal degradation behavior of pyrolysis of extracted lignin. We also turn waste into energy by using lignin away from harvesting the polysaccharide fractions. For the conclusion, increasing heating rates from 5 to 20 degrees Celsius shifts the thermal degradation profile to a higher temperature range. The DGG analysis peaks at 320, 359, 345, and 452 degrees Celsius heating rates. This means that at these temperatures, the thermal degradation is at its highest. The average active energy needed for pyrolysis is 66.68 kilojoule per mole. The pyrolysis of EFP lignin is governed by diffusion reaction, and the EFP lignin shows potential in the thermochemical application. Now, acknowledgement, I would like to thank the Swinburne University of Technology for their. I also want to thank the laboratory in Brin, which is in Indonesia, and also a.k.a. POPSIG. These are my references. Thank you.